So in the last class, we did stop at a point where we said that for your EM wave in free space, again, today's and tomorrow's lecture is going to be even more mathematical. And then I think rest of the syllabus is not so more mathematical. So we were talking about electromagnetic waves in the free space. And in the last class, we stopped at a point where we said that your magnitude of electric field is 3 times magnitude of magnetic field. This was where we stopped in the last class. We also said that your E we did take to be a vector. And we said that we are going to assume that this vector is possibly in all the 3 directions, X, Y, and Z. And we said that this is going to be something of this form. We have preferred the exponential form rather than sine or cosine. The reason being that it's easier to discuss exponential function time and again. We also said that if I take the modulus of this E, which will be nothing but the square root of this vector with the complex conjugate of this vector, if you take the dot product and then take the square root of this would be nothing but this would be equal to your E naught basically. Similarly, for the B, also we said that we are starting with the assumption that your magnetic field can also be in the all possible directions and it will have the same form as is the electric field. And similarly for the magnetic field, as was the case of electric field, you can determine the magnitude and that magnitude will come out to be this here. This was where we stopped in the last class. We had done up to this point here. There is something else also which is defined as space impedance. Impedance because it has the units of resistance and this is usually denoted by capital Z. This space impedance is defined as E over H, where H is nothing but the magnetic field that you are going to apply, and this is equal to, if you are talking about the free space, you know the relationship between B and H. B is equal to mu naught times H if you are talking about the free space. And even if I'm not putting the arrow, they are of course the vector quantities here. So far we have only talked about E and B. Now we have H here. We'll talk about the physical significance of this space impedance also. Let's put the value of H first. H is nothing but B upon mu naught. So I can write this as mu naught into E upon B. And these are the modulus here. So this is simply the mathematical definition of the space impedance here. Now from here, if I want to put the value of modulus of E and modulus of B, this is nothing but modulus of E naught over modulus of B naught. Because this exponential term, whenever you will take the complex conjugate, minus aayega aapka or plus minus will cancel each other out. We derived this expression. So from here, we can say that E naught upon B naught is equal to C, right? So that means I can write this as mu naught times C here. C, from the previous, I think last to last lecture, we said that C was equal to square root of mu naught and epsilon naught. If you plug in those values here, then what you will get is this expression here. You can further solve it and this is what you will get eventually. If you put the value of mu naught, which is the permeability of the free space, and if you put the value of epsilon naught, which is the permittivity of free space, then what you get would be something equivalent to 376.7 ohm. The units will be the units of resistance here. And that is why it's called as space impedance. Now the question comes that you are talking about a space which is free of any kind of charges and any kind of currents. Then how do you come with something called as space impedance here? Now let's assume that if there is nothing present in it, if you are talking about absolute vacuum, you would expect Z to be 0. One could argue that because there are no charges, no currents, nothing is present there. So your space impedance should be equal to 0. Now if you talk about Z being 0 here, by definition here, Z can be 0 under 2 scenarios. One, if your E is equal to 0. Right? If your numerator is 0, then Z is equal to 0. But if your numerator is 0, then your E is 0. You will simply have the magnetic field, and this will not be electromagnetism, because in electromagnetism you need to have both electric as well as magnetic oscillating fields. So your E cannot be equal to 0. The second scenario in which your Z can be equal to 0 is when your denominator becomes equal to infinite. That means your H or magnetic field becomes equal to infinity, which is an unphysical condition. You cannot have infinite magnetic field, which this cannot be realized physically. So you cannot have E0, you cannot have H infinity, hence your Z cannot be equal to 0. What does this physically signify? This signifies here you have C here, which is basically the speed of light. So this space impedance, if you are saying that there is no resistance, then why is not the speed of light infinite in free space? What is it? If there is no resistance, then your speed of light should be infinite in that case. So having this finite value of space impedance, in a way, you can understand it simply by saying that this puts a limit on the speed of light, so that your speed of light cannot exceed 3 into 10 raised to power 8 meter per second. If your space impedance would have been 0, then there wouldn't have been any limit on the speed of light. So this is the physical interpretation of having a finite space impedance, even though there are no charges, no currents, nothing is present in the system. We are talking about an absolute free space or vacuum. Even then, you have a finite value of the resistance or impedance there. Now we are going to move to conducting medium. So far, we were talking about the free space. That means there are no charges, no currents. So before we go to the conducting medium, and in the conducting medium, eventually, we will divide our medium into poor conductor as well as good conductor. Good conductor could be, for example, your copper, silver, etc. They could be good conductors. Poor conductor could be, for example, wood or water. And here the definition of good conductor and poor conductor, you will see, will depend on the frequency of electromagnetic wave. Something which could be a good conductor for particular frequency may be a poor conductor for another frequency. Because remember, the spectrum of electromagnetic wave is so wide. It has a huge range of frequencies. So depending on the frequency, something can be a good conductor or something can be a poor conductor. The frequency will be the deciding factor. We'll see that how does that happen. But before we go there is something which we derived earlier, equation of continuity, which is basically based on the principle of local charge conservation. We derived this equation before Maxwell's fourth equation. And this equation basically said that your del dot J is equal to minus curly rho by curly T. This is what this equation did say that. And both of them did, this equation basically came from when we said that your I is equal to minus dq by dt. If there is current flowing out of somewhere, that means charges present in the system are reducing as a function of time. So this equation of continuity equation was derived from here. We derived it 2 times. If you don't remember, you can go back to the previous lectures and have a look over there. Please mute yourself. J is defined as I over A. If you are talking about the magnitude, there is something called as microscopic form of this, which basically talks about it in the vector term, where you say that J is equal to sigma multiplied by E, where sigma is the conductivity and which is nothing but 1 upon resistivity. E is the electric field. I think you are aware of both of the terms over here. Now in this expression, in this equation of continuity, I can say that del dot sigma E is equal to minus curly rho by curly T. Sigma constant hai, because it's conductivity, you can take it out. And then I can say basically that your sigma del dot E is equal to minus curly rho over curly T. Remember Maxwell's first equation. Now we are talking about a medium. We are no longer talking about the free space. So we are talking about a medium, and let's say mu is the permeability of that medium, epsilon is the permittivity of that medium. Mu naught was the permeability of the free space and epsilon was the permittivity of the free space. Now we are going to replace mu naught and epsilon naught with mu and epsilon, because we are now talking about a medium, and that medium will have a different value of permeability and permittivity as compared to the free space here. According to Maxwell's first equation, del dot E is equal to rho upon epsilon. It is epsilon naught if you are talking in free space, but if you are talking in a medium, then epsilon naught will be replaced by epsilon here. So that means this equation here I can write in this form also. Rho upon epsilon is equal to minus curly rho over curly T here. This also means that I can write this as, I'm taking minus on this side, sigma upon epsilon curly T is equal to curly rho over rho. I have collected the terms which corresponded to charge density. Rho is your charge density, which is charge per unit volume. This is your rho here. Sorry about that. So I have simply collected the same terms on one side here. Now what I can do is that I can integrate on the both sides. Let's say at time t is equal to 0, your charge density was rho naught, and at time t is equal to t, this became equal to rho here. So this rho naught is the charge density at time t is equal to 0, and at time t is equal to t, this became equal to rho here. You can integrate on both sides. 1 upon rho multiplied by curly rho would be equal to, integration of that would be ln of rho with the limit rho naught over rho. Now sigma upon epsilon is constant, you can take it out. Integration of curly t or dt would be equal to t, limit t और 0 पुट करेंगे तो आपको सिंपली यहाँ पे t मिल जाएगा. यहाँ पे लिमिट अगर आप पुट करोगे, what you will get is ln of rho minus ln of rho naught is equal to minus sigma upon epsilon into t. इसको आप फर्दर राइट कर सकते हो, ln a minus ln b is equal to ln a over b. So आप इसको फर्दर ऐसे राइट कर सकते हैं. दोनों तरफ exponential अगर ले लोगे, so exponential on the left hand side will cancel ln, and on the right hand side you will get e raised to power minus sigma upon epsilon into t. So what you will get would be rho upon rho naught is equal to e raised to power minus sigma upon epsilon t. If you take exponential on both sides, left hand side as well as on the right hand side. So this is what you will get here. That means here rho, which is as a function of time, of course, is equal to e raised to power minus sigma upon epsilon t. What does this mean physically now? This means that if you have a material, and let's just material may you place some amount of charge, and that charge would correspond to charge density being equal to rho naught here. Imagine a pipe of copper, and if you place a charge on that copper wire or copper pipe, what would happen to that charge? Is that charge going to stay wherever you have put it, or is it going to redistribute itself? This equation basically dictates that if you place a charge on anything, the charge is going to behave in this fashion. It is going to redistribute itself till the point there is some kind of equilibrium, and your curly rho by curly t, which was the right hand side in the continuity equation, becomes equal to 0. Unless this becomes equal to 0, your charge will keep on moving from the place where you have placed the charge on the conductor, whether it's a good conductor or the poor conductor. Depending on the conductor that you are talking about, it may be a very good conductor. If it's a good conductor, then its sigma is going to be large, right? Good conductor means its conductivity is going to be very large. If its conductivity is very large, then the charge is going to decay exponentially very fastly, which means that the charge will distribute itself on the copper pipe or copper wire very fastly. On the other hand, if it's a poor conductor, let's say if it's a wood, for wood, your conductivity, which basically means that sigma would be very less. That means if you place a charge on the wood, it is going to redistribute itself in a very, very long amount of time. because this equation basically states that, which is the equation of continuity here. So,
Ma'am, could you please repeat this, what this equation tells us?
yeah, sure, I can do that. This equation tells you, suppose on a piece of material, you placed a certain amount of charge on it. So remember, rho naught was your charge density at time t is equal to 0. At time t is equal to 0, let's say you had a wire of copper here and you have placed this amount of charge at this point at time t is equal to 0. Now, let's say after 2 or 5 seconds, you measure the charge density here. Is it going to remain the same? Or the charges are going to redistribute themselves? If they are going to redistribute themselves, then how fastly or how slowly they are going to redistribute themselves is basically decided by this equation here.
Okay,
The
ma'am.
charge density at this point after time t is given by this expression here. Now imagine a case where your sigma is very large, which will happen in the case of very good conductors, when your conductivity will be very large. What would happen? This will decay very fastly. Exponentially decaying function would decay very fastly in this case if your sigma is very large. This means that at this point, your charge density will decay very fastly. That basically means that yahan pe, in the case of good conductors, if you place a large amount of charge at one point, the charges are going to redistribute themselves. And that will happen very quickly if it's a good conductor. On the second hand, if it's a poor conductor, then your sigma is going to be very small. If your sigma is very small, तो ये जो आपका exponentially decaying function है, ये बहुत slowly exponentially decay करेगा. This means that अब अगर आपने यहाँ पे अगर चार्ज प्लेस कर दिया है, तो वो चार्ज जो है वो यहीं पे बहुत large amount of time के लिए it will stay there and it will redistribute itself at a very, very slow rate because this exponentially decaying function is going to be a very slowly decaying function. If the material that you are talking about is a poor conductor, because then your sigma is small. So this is the physical meaning of this expression. It basically decides, अगर आप कोई भी material ले लो, उसके ऊपर अगर आप charge place कर देते हो, what happens to that charge? How fastly that charge will be distributed on the complete material that you have taken. That is decided by this expression over here. Now there is something which is called as characteristic time or charge relaxation time.
मैम इसमें एप्सिलॉन किसका मीडियम का होगा?
अगर आपने यहाँ पे कॉपर लिया तो कॉपर का होगा और अगर आपने यहाँ पे वुड लिया है तो वुड का होगा.
ओके मैम.
There is something called as characteristic time or relaxation time. Usually denoted by tau. It is defined as the time in which your charge density decays to 1 by E of its initial value. This means that when your time becomes equal to characteristic time, your charge density would become 1 by E of the initial value, and your initial value was rho naught. Looking at this expression here, you can clearly tell that when your T is equal to epsilon over sigma, जब आपका T epsilon over sigma के equal हो जाएगा, तो sigma upon epsilon उसको कैंसिल कर देगा और आपके पास e raised to power -1 बच जाएगा यहाँ. So when T is equal to epsilon over sigma is basically your time, which is called as characteristic time or relaxation time. And this is the time in which the charge that you have placed here, let's say you did put some 50 units of charges here. After this much amount of time, यहाँ पे जो charge बचेगा, that would be 1 upon E of 50. This much amount of charge will be left here. And this is called as characteristic time or relaxation time. Again, if it's a good conductor, कंडक्टिविटी इज गोइंग टू बी वेरी लार्ज, आपकी सिग्मा बहुत लार्ज होगी, आपका कैरेक्टरिस्टिक टाइम या रिलैक्सेशन टाइम है वो बहुत स्मॉल होगा, which basically means that charges जो है वो बहुत fastly redistribute हो जाएंगे. On the other hand, if it's a poor conductor, then your sigma is small, then your characteristic time or relaxation time would be very large in that case, which again means that your charges are going to redistribute very slowly in that case. If you take an example of good conductor here, for example, for copper, this characteristic time is 4.5 into 10 to the power minus 19 seconds. If you place any amount of charge on the copper, within this much amount of charge, the charge will be reduced to 1 by E of the initial amount of charge that you have placed on the copper. This is how fastly the charges are going to be redistributing themselves. This basically means that you can assume that in the conductor, there is going to be no charges present. All the charges are going to be present on the surface of the conductor. Inside the conductor, you can say that there are no charges. So if there are no charges inside the conductor, that means you can say that the charge density is 0. So from this equation here, now we are going to move on to the conducting medium. I'm repeating that because we said that in the conducting medium, there is something called as characteristic time or relaxation time. So we can assume that all the charges are going to be on the surface of the conductor. There are no charges inside the conductor. If there are no charges inside the conductor, then your charge density is 0 inside the conductor. Now, let's say that mu is the permeability of this conducting medium that we are talking about, and epsilon is the permittivity of the medium that we are talking about. If we talk about Maxwell's equation, in conducting medium, the first equation says that del dot E is equal to rho upon epsilon naught. But we said that there is no charges present in the conductor, so this becomes equal to 0. The second Maxwell equation says that, sorry, it should not be epsilon. This has to be, does not have to be epsilon naught. This will be epsilon here, because now we are talking about a finite medium which has a different permeability and permittivity as compared to your free space. Second equation says that del dot B is equal to 0. Third equation says that del cross E is equal to minus curly B over curly T, which will stay as it is. The fourth equation says that del cross B is equal to mu J plus mu epsilon curly E by curly T. In the free space, we used mu naught J plus mu naught epsilon naught. Now we are going to replace it with the permeability and permittivity of the medium that we are talking about. So these will be now our 4 Maxwell's equation that we are going to play around with. As we did for the free space, we'll do exactly the similar thing in this case also. Remember, in the free space, what I did is that we did take equation 3, we did take equation 4, and we did take curl of equation 3 as well as equation 4 to get the second order differential equation for electric field and the magnetic field. We'll do the same here also. The equation 3, which says that del cross E, and again you can do any one of them. The second you can say simply similarly, but I'll just, for the sake of completeness, simultaneously we'll do the second also. But if it comes in the exam, you do not need to do both of them. You can simply do one and say that similarly on the second equation here. This is your third Maxwell equation. This is your Maxwell equation 4. Now, let me remind you the difference between the free space and the conducting medium, apart from mu and epsilon being different, is that in the free space, your this term was also equal to 0, because we said that free space is free of any kind of charges and currents. So when we are talking about free space, your this term was also equal to 0. But in the conducting medium, you have a finite current density. Even though the charges inside the conductor are 0, but the current density is going to be a finite number here. So this will be the difference in your Maxwell's equation in free space and conducting medium, that you have this term retained when you are talking about the conducting medium. Coming back to these equations, equation 3 and equation 4, take curl of the equations. And similarly in this case also. So what you will get is del cross E is equal to minus curly by curly T del cross B. I have taken del inside reason, time and space. They are independent coordinates. Similarly, you can do the same for fourth equation also. I'm again going to prove that you are going to get the same equation for electric field and the magnetic field. In the conducting medium also, you are free, as was in the case of free space, electric field and magnetic field, they are going to behave in the similar fashion. So I can write here also del cross E. I have taken curl of equation 3 and equation 4. Del cross J, mu is constant, take it out. Mu epsilon curly by curly T is independent of del operator. Can take those also out. वेक्टर ट्रिपल प्रोडक्ट यहां पे अगर आप लगाओगे BAC माइनस CAB, यू गेट डेल डॉट E माइनस डेल डॉट डेल E माइनस करली बाय करली T. एज वी डिड फॉर फ्री स्पेस, यहां पे जो डेल क्रॉस B की वैल्यू है, प्लग इट फ्रॉम इक्वेशन नंबर 4. इक्वेशन नंबर 4 टेल्स यू व्हाट इज द वैल्यू ऑफ डेल क्रॉस B, so that we have everything in terms of electric field. Do the similar for this equation also. You will have del dot B minus del dot del B mu. J is nothing but sigma times E, right? So sigma को आप बाहर लिख दीजिए, यहाँ पे आपके पास में del cross E बच जाएगा, क्योंकि सिग्मा कांस्टेंट है. सो क्रॉस प्रोडक्ट से भी आप बाहर ले सकते हो, उसका विद रिस्पेक्ट टू स्पेस डिफरेंशिएशन से भी कोई लेना देना नहीं है. टेक सिग्मा आउटसाइड एंड आई हैव सिंपली सेड दैट J इज इक्वल टू सिग्मा E फ्रॉम हियर टू हियर प्लस म्यू एप्सिलॉन करली बाय करली T. डेल क्रॉस E की वैल्यू जो है वो इक्वेशन नंबर 3 से प्लग इन कर दीजिए. इक्वेशन नंबर 3 सेज दैट डेल क्रॉस E इज इक्वल टू माइनस करली बाय करली T. Let's first finish this side of the equation. Del dot B is equal to 0 as per Maxwell's second equation. You will have minus del square B is equal to mu sigma del cross E, again from equation number 3, is equal to minus curly B by curly T. Minus mu epsilon curly by curly T. So you have curly square B over curly T square. तीनों तरफ माइनस, तीनों में टर्म्स में you have the negative sign, minus here, minus here, minus here. So I can write simply in this form also. Now this is the second order differential equation which has only the magnetic field here. There is no electric field present in this case. Let's talk about this equation also. Del dot T is equal to 0 in the conducting medium. You have minus del square E minus mu, take out. J is nothing but sigma times E by curly T minus mu epsilon curly square E by curly T square. Again, minus is there in all the three terms. You can write this as del square E is equal to mu. You can take sigma out, curly E by curly T plus mu epsilon curly square E by curly T square. This equation and this equation, both of them are exactly similar to each other. The only difference is in one case you have electric field, in the second case you had the magnetic field. So you can either prove this side, and you simply can write that similarly by taking curl of equation 4, you can prove the equation or the expression for the magnetic field. Or you can do the expression for the right hand side and then write it similarly for electric field. You will get the similar expression here. The only difference is that you have to replace E by B in the expression here. So even in the conducting medium, if your equations are exactly similar here, that means your electric field and magnetic field are going to behave exactly in the same way. क्योंकि दोनों की आपकी differential equation exactly same है. So their behavior has to be exactly similar to each other. But now the good thing is that since we have already proved that your electromagnetic waves are transverse in nature. So when I'm going to write the solution, I'll write a simpler solution now. In the free space, because we haven't proved that electromagnetic waves are transverse in nature, so the solution of the equation I wrote in a quite complicated way, where we said that your electric field can be in every possible direction, magnetic field can be in every possible direction, and your direction of propagation could be every possible direction. But because now we have proved that electromagnetic waves are transverse in nature, so what we are going to do is that I'm going to say that let's assume that my electric field is only restricted in the y-axis. It does not have any x component or z component. And let's say that e raised to power iota, the term that you write here with k decides your direction of propagation of wave. Now, if I'm saying that y is the direction of electric field, I cannot write y here now, because then I'm saying that direction of propagation is also y and the electric field is also in the y direction, which is not allowed here. So I can either take now the wave propagating in the x-axis or in the z-axis. So let's take it along the z-axis. Similarly, magnetic field now, we have already taken the y and the z here. So magnetic field has only one choice, that it has to be along the x-axis. This will be now your expression for the magnetic field. What we need to do now is that plug in the value of this electric field and this magnetic field. And now this electric field as well as magnetic field are function of z and time, because you only have the z dependency. Similarly, your magnetic field is also a function of z and time only. Now what we have to do is that we need to put these value of electric field and magnetic field into these equations here and see what do we get here.
Ma'am,
Hanji.
ma'am, in electric field you have written y cap, but in the like exponential part we wrote iota z minus kz minus omega t y.
So this term here tells you direction of electromagnetic waves. And this tells you your direction of electric field.
Okay, ma'am.
So direction of propagation of electromagnetic wave, if I have chosen it to be z direction, so magnetic field may be, we have to take kz only. You cannot take it ky, क्योंकि आप कह रहे हो y direction में तो आपका electric field है. You cannot take kx because x is the direction of the magnetic field. तो आपके पास में सिर्फ और सिर्फ z एक्सिस बचता है डायरेक्शन ऑफ प्रोपगेशन के लिए, अगर आपने ये कह दिया है कि आपका इलेक्ट्रिक फील्ड y में है, मैग्नेटिक फील्ड x में है. बट ऐसा कोई हार्ड एंड फास्ट रूल नहीं है. आप चाहो तो इलेक्ट्रिक फील्ड को x में ले लो, मैग्नेटिक फील्ड को z में ले लो, डायरेक्शन ऑफ प्रोपगेशन आप y एक्सिस भी कर सकते हो. दैट इज आल्सो फाइन एज लॉन्ग एज ये तीनों चीजें एक दूसरे के म्यूचुअली परपेंडिकुलर हैं. फर्क नहीं पड़ता आप कौन सी डायरेक्शन किसके लिए पिक करते हो. Only condition is that they have to be, and it is a must condition that they always have to be perpendicular to each other. Now if I go back and I'll just do it for the electric field, you can do it for the magnetic field by yourself if you want. what I'm going to do is that I'm going to put this value of electric field in this equation over here, and we'll see what do we get there. So this equation here, let me rewrite this equation. And before doing that, let me erase that. Otherwise I'll be. So from the previous slide, our equation is del square E being equal to mu sigma curly E by curly T plus mu epsilon curly square E by curly T square. Del square E. Del square is nothing but curly square over curly x square plus curly square by curly y square plus curly square over curly z square. Electric field E0y, y unit vector e raised to power iota kz minus omega t. Now if you take this term inside here, with respect to x अगर आप इसका differentiation करोगे, there is nothing as a function of x here. So with respect to x, it would be 0. Similarly, if you do the derivation with respect to y, remember y here represents a unit vector, right? E0y is the magnitude of electric field along the y-axis. So both of them, you cannot differentiate with respect to y here. And this exponential term does not have any y component either. So this will also be equal to 0. Now, if you do its differentiation with respect to z, what you will get is E0y, y as it is, and you need to differentiate this exponential function 2 times with respect to z. एक बार अगर आप differentiate करोगे तो iota क्या आएगा? Exponential as it is आ जाएगा. Second time differentiate करोगे एक और iota क्या आ जाएगा? And this is what you are going to get. Now, we also need its derivative with respect to time also, first order as well as the second order derivative. If you take the derivative of this with respect to time, you are differentiating basically. Let me do the second order derivative itself, or let's first do the first order derivative. Time की जो term है, only this is the term which contains time here. With respect to time, अगर आप करोगे, what you will get is minus iota omega, and the rest of the term will come as it is. Second time, with respect to अगर time आप derivative करोगे, what you will get is minus iota omega square, and the rest of the term would be as it is. Now in this equation number 1, I can plug in the value of del square E from equation 2. I can plug the value of curly E by curly T from equation 3. I can plug in the value of curly square E by curly T square from the equation 4. And then you can write your equation 1 can be written as del square E is nothing but E0 y unit vector I k whole square e raised to power iota kz minus omega t.
Ma'am, please show the previous slide once.
हाँ जी बच्चे.
Thank you, ma'am.
Okay. And mu sigma curly E by curly T. So I'll write mu sigma curly E by curly T is minus iota omega E0y y unit vector e raised to power iota kz minus omega t. And then I had the last term where I had mu epsilon here plus mu epsilon and then minus iota omega whole square E0y y unit vector e raised to power iota kz minus omega t. That basically means that I can cancel E0y From here, I can cancel e raised to power iota kz. It's there in every single term here. Each one of them is along the y axis. So I don't need to really write the y unit vector here onwards. I can simply say that iota k whole square is equal to minus iota omega mu sigma plus minus square plus iota square will be minus here. So you will have minus here also. You will have mu epsilon omega square. From here, minus k square is equal to minus iota omega mu sigma minus mu epsilon omega square. Minus ko, you can take it out and write it in this form. This is equal to basically k square now. Now if you have square of something, and if you have square of something and that has a real part and an imaginary part, that would mean that this term has to be made up of two parts, one of which is going to be real and the other one has to be imaginary, right? That means this has to be equal to this one. There is no preference for writing k plus and k minus. You can simply write it alpha plus iota beta also. That is also absolutely fine. There is no reason. I'm writing here the subscript plus and minus. There is no reason for writing that. Just because I'm writing it in terms of k, that's why I'm writing here plus and minus here. But you can take any term here. Let me repeat that. If the square of something is made up of two terms, one of which is real and the other one is imaginary, that means that term has to have a real part and an imaginary part here. And I think I'll stop here. I'll start from this equation here. Please note down this equation somewhere and then we'll start from here onwards. And the electric field and the magnetic field expression also. These two expressions also. We'll plug the value back in here and we'll draw some conclusions, some physics from there. So we'll start from here in the next class. Anyone has any doubts in today's class? Okay, I'll upload the lecture on LMS maybe in the next half an hour or so.
मैम k plus और k minus का मतलब क्या है?
K plus और K minus का क्या होगा? Sorry.
मैम k is equal to k plus.
I'm saying
k
that
minus.
K is made up of two components. One is real, another one is imaginary. K plus और K minus, क्योंकि मैं K को K की form में ही लिखना चाहती हूँ. That is the only reason I'm writing it in this form.
Okay.
हाँ जी.